Hey everyone! In this video, we're going to be talking about applications of exponential functions. And specifically, we're going to be able to talk about how I model real-world scenarios in word problems that model both exponential growth and modeling exponential decay. So we're going to go ahead and start with problems that model exponential growth. And I'm going to write out a formula for you in a second, but I want to let you guys know that you should pretty much recognize this formula already. So this formula very closely resembles the formula for compound interest, which was the last application of exponential growth that we talked about. So our formula is going to be f of t is equal to a times 1 plus r to the t. So again, this should look very familiar. Some of those letters in there are different. We're used to seeing a P right here instead of an A, and we're used to seeing a divided by n and an n in the exponent, but there are no compounding periods here because it isn't talking about compounding interest. But basically, this is generally what we are looking at. So I'm going to go ahead and define all of these for us. So A represents the initial value. And that makes sense to us, hopefully, because the A is where the P was in the last equation we learned about compound interest, and P stood for the principal or the initial value. So the initial value in my problem is still always going to be out in front of those parentheses. The R still stands for rate, but in this case, we're specifically going to call it the growth rate instead of calling it the interest rate because I'm not talking about interest anymore. Okay, so that says interest rate. You can't really see it over there, but okay. And then T still stands for time in years. Okay. Now that we have this equation, we're going to go ahead and we are going to use it to model this situation here. So looking through our problem, the original value of an investment is $1,800. So I already am told the initial value, so I'm going to write out that A stands for 1,800. If the value has increased, now that tells us that this is an exponential growth problem, which you can probably assume by the fact that we just learned the exponential growth formula, right? But in the future, we are going to be able to identify that. So think about increase does mean growth. And it's increasing or growing by 7% each year. So I'm going to go ahead and write that my rate is 0.07. Remember that to convert a rate from a percent to a decimal, which you always have to do to substitute into the equation, all you do is you divide it by 100, and that gives you 0.07, which is why I wrote that as the rate. And then the other piece of information we have is that the value, we're looking for the value after 15 years. So that would be t equals 15. Before we even get there, though, notice that this question asks us to write an exponential function to model the situation. So what that is asking us is to write a generic function that can be used to find the value at any given time. So when I go to plug in these values in the first place, I'm actually going to leave t still there because t is my variable. And that is how I write the function that models the situation. So I'm going to go ahead and replace a with 1,800. 1 plus is still there. The rate is 0.07. And like I just said, I'm still going to include the exponent and write it as t. And this is the generic model that can be applied to the situation at any point in time. I could use this to find the value after 2 years, 15 years, after 100 years, right? I could plug in any value for t. But in this example, it's asking me to plug in 15. So I am going to specifically plug in 15 for t as my next step. So I'm literally just copying everything the same, but my exponent is 15. And then I can go ahead and that is certainly not what I wanted. I can type this into my calculator. So you probably can't see the whole thing on the screen anymore, but I am just going to go ahead and type. Right? Remember the caret is the exponent. Okay, and it gives me this answer. So I'm going to go ahead and I'm going to record that on the screen. We are talking about money here, just like we were in the last topic. So I'm going to ask that you still round to 2 decimal places, right? We're going to round based on the context of the problem. And anytime you're dealing with money, it makes sense to round to the hundredths because a penny or a cent out of 100 cents, right, is the smallest unit in money. So that is our answer here. Now we're going to look at another example. This one, again, as we read through, we're just going to sort of pull out that information that is important. So it says in 2002, there were 972 students enrolled at Oakview High School. So that's my initial value, right? Way back in 2002. Y'all probably weren't even born back then, which is kind of wild. But there were 972 students enrolled at Oakview High School. Since then, the number of students has increased. So this is an exponential growth by 1.5% each year. And if I were to divide 1.5 by 100, that would give me 0.015, which becomes my rate. Then it asked me to write an exponential function to model the situation, then find the number of students enrolled in 2014. Okay, so before I even deal with time, I'm just going to write out the model because I know in order to write the function that models the situation, I don't even need to know t yet. So f of t equals, and then I'm substituting 972 in for a. I have 1 plus my rate, and then to the exponent of t. Okay. After that, I am going to go ahead and I'm going to plug in t. But I need to read this problem and figure out what is t. So it asked me to find the number of students enrolled in 2014. So some people will be tempted to write 2014 out. But think about this problem. We started in the year 2002 and we are ending in the year 2014. So I'm trying to think about the number of years that has passed between those two. And in this problem, they're giving me a hint that says 12 years later. So we can use that to indicate to us that t is in fact 12. But if you were ever given a problem where it doesn't have that hint, but it has a beginning year and an end year, just know that you subtract the two numbers to figure out how much time passed between them. Now that I know that though, I can go ahead and I can plug it back into my equation. Once again, I am just rewriting the equation exactly as is from before, but this time, instead of writing t, I am writing 12. Okay. And by this point, hopefully y'all are pretty solid with typing things in the calculator, so I'm not going to show that part, but I will tell you that when you type that in the calculator, and you guys can go ahead and double check my work at home, but when you type it in, that would come out to 1162.14 if you round to two decimal places. This is probably what a lot of you guys would say, or a lot of you guys would even take this number and you'd be like, oh yeah, I got to add the dollar sign there. But before you do that, let's take a minute and let's think about this in context, right? So do I really want a dollar sign there? And do I really want to round to two decimal places or to the nearest hundredth? Well, looking at this problem, we're not actually talking about money here. We're talking about students, right? There were an original 972 students enrolled, and my question that it was asking was to find the number of students enrolled in 2014. So it's asking for a number of students. So if my question asks me for a number of students, I'm not going to respond with a number of dollars. That just simply isn't answering the question. So the way I set up this formula was to provide me with a number of students. So this number here is actually indicating the total number of students. However, you can't have 0.14 of a student, right? Like that is literally a partial child. You don't have that. That's not a thing. Okay, we are counting whole people here. So I'm actually going to round this to the nearest whole number. Okay, and again, rounding is something you need to figure out from the context of the problem and what makes sense in that instance. With money, it makes sense to round to the hundredth. With people, it only really makes sense to round to the nearest whole person. And then in order to make sure I'm including my units and answering in context, I would say that it is 1,162 students are now enrolled at Oakview High School. Now we're going to get on to some exponential decay. So there is a space here for me to write another formula, and I am going to write that formula out. But honestly, I'm going to encourage you guys not to pay a ton of attention to this formula, and I will explain why in a second. So this formula looks almost exactly the same as my formula did for exponential growth, right? And all of these values are basically defined the same way, except for rate, this is a decay rate. I'm no longer growing, so it wouldn't be a growth rate. I'll call it the decay rate, okay? But other than that, everything here is the same, except for the fact that I am subtracting my rate instead of adding it. Well, that makes sense in context to me, right? Because if I'm growing, it makes sense I would have more, right? Like you're taking one and you're adding a certain rate to it. So if I wanted to increase by 4%, it makes sense that I would take one representing 100% and I'd increase it by 4% by adding that. Whereas if I'm decaying and I want to decrease by 4%, I would subtract the 0.04, right? To give me the fact that I'm only going to have 96% at the end of a year. Right? So think about this logically and what makes sense. Really, what you're doing here, you don't have to memorize two different formulas. I personally always just consider the growth formula, and then I think about whether it would make sense for me to have a negative or positive rate in that context. So if I am growing or increasing, my rate would be positive, and if I am decreasing or decaying, my rate is negative. So essentially, I'm just subtracting it. With that being said, if you want to write down both of these formulas and have those committed to memory, that is your choice. But that's not how I'm going to go about solving these. So going through this problem then, an investment of $12,000 is losing value at a rate of 4% each year. So it's an investment of $12,000. So that's my initial value. And it is losing at 4% each year. So I kind of go ahead and think about that as a negative rate, like negative 0.04. Okay, you could think about this and write it as a positive, and then you could still go back and just subtract when you get to the formula. So again, that's sort of a choice that you can make. But then my goal is going to be to find the value after 9 years. So t is 9. When I then go to write my formula here, I'm again plugging in that initial value where it always goes. And then when I get to 1 plus my rate, because this is a decay, right, I could either memorize that it is minus the rate, or I could just think logically, well, I'm losing value, so obviously I'm going to subtract that rate, right? So hopefully that makes sense to think about it that way. My next step is to find the value at time t equals 9. So again, I'm copying, 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 and then I'm just going to write a 9 in the exponent. Again, y'all at this point should know how to type this in a calculator, so I'm just going to continue doing that on my own and then showing you, and that'll give you $83,310, $88,310.41. And this, if you look in the problem, it is talking about money, so it does make sense to round to 2 decimals and to leave that dollar sign there. So with that problem closed, we're going to look at another example of exponential decay. Again, this formula here is written as the decay model. So you see this minus r. Again, it's your choice. I literally don't think about it as two separate formulas. I just think about it as one. And that makes it easier for me to remember the formula. But as I approach this problem, I'm looking at Mark just bought a brand new car for $35,000. So that's the initial value, how much he bought it at. And then it says, if the car depreciates in value by 8% each year, write a function to model the situation. So I see the rate is 8%. 8 divided by 100 is 0.08. So I know that's my rate. But let's look at this word here. The word depreciate. If you don't know what that means, basically depreciate means to lose value. So think about the context of this problem. Someone buys a new car. Well, you know how used cars, they sell for less than a new car does. So if I buy a new car, it is going to lose value over time, right? If I want to sell my car in 2 years, it's not going to be worth the same as it is today. So depreciation is basically when something loses value. You hear this a lot when it comes to cars or equipment or machinery that a company might own, right? In the business world, people talk about depreciation all the time. So if you ever end up going to business school or something, you will do a lot of calculations that have to do with depreciation. But basically, depreciation just means it indicates a decay or a decrease. If you ever have trouble remembering what that word means, it starts with DE, just like decay and decrease. So hopefully that prefix helps you remember that they all have the same meaning. All right. And then looking at the last part of our question, it says find the value of the car after 15 years. So that's going to be my time. So I have f of t, and then plugging in 35,000 for a, 1 minus 0.08 to the t. That's my exponential model that models this at time t. And then to answer the other half of this question, which is specifically what is the value after 15 years, that is when I actually plug in a number for t. And when I do this, again, you guys should be double checking and practicing typing in your calculator at home, but that is going to come out to $10,020.41. Again, we are talking about money, so I round to the 100th place. Okay. We're going to do 2 more problems, and for these last 2, I'm just going to have this general growth rate formula written at the top, and we're going to have to work through the problem to figure out if this increases or decreases, whether it is exponential growth or exponential decay. So that's just sort of one additional thing you have to do as you go through the problem. So as I read, the current population of Rockville is approximately 68,000 people. So 68,000 becomes our initial value. If the population increases, okay, so I know I'm looking at a growth because it's increasing, it's getting bigger, by 1.2% each year. So I divide 1.2 by 100, I get 0.012. Now it asks me to write an exponential function to model the scenario. So f of t, and I have my a value of 68,000, just substituting that in. And then I have 1. And remember, I was given a growth. I'm talking about increasing. So I'm going to go ahead and I'm going to add that rate of 0.012. And then raising that to the t. Okay. And then I can move on to this last part of the problem that says, then find the population of Rockville 10 years from now. So t is equal to 10. Thus, I'm going to find f of 10 and rewrite everything the same exact way, except for I am now going to change my exponent of t to a 10. And that comes out to 76,615.04. But I need to think in the context of my problem. Does this answer make sense? Should I be throwing a dollar sign up there for units? Like, I don't know. Well, look back in the problem. My initial value, 68,000 people. Then it asks find the population of Rockville 10 years from now. Population means the number of people living somewhere, right? So I'm looking at people here, not money. So can I have 0.04 of a person? Probably not. I would hope not. I don't want to see that much of a person, okay? I want to see whole people. So we're going to go here and we are going to say 70. Oh, why did I write a dollar sign? Oh, Miss Warren, you're making a mistake. What are you doing? You're confusing us. Ah. Okay. That was an accident. Anyways, but so this is people. So I'm going to have a whole number and I'm going to make sure the units are correct. So my population after 10 years is 76,615 people. And that takes us to our very last problem of this video. So once again, we are going to have to determine whether it's a growth or decay, and that is something you will literally always have to do from now on. I'm not going to just straight up tell you which, just presenting you with this generic formula. But RM just bought a printer for $2,400. If you are wondering, doesn't that sound like a lot for a printer? I actually did some research on this, and that's very cheap for an industrial size printer. So the printers and copiers your teachers use when we're actually in the building, they cost a lot of money. Apparently the average is $3,000 to $15,000. So this is actually a cheap one. But anyways, RM just bought a printer for $2,400. So that is my initial value. If it depreciates, okay, depreciates, remember, that sounds sort of like decay. So I know that indicates an exponential decay. It depreciates at a rate of 12%. 12 divided by 100, 0.12. Write a function to model the scenario. So again, just as always, I plug in A, my initial value, and then I have to figure out, okay, this was a decay. So remember, I'm decreasing, I'm getting smaller, and so that indicates to me that I'm going to subtract the rate before raising it to the exponent of t. And then it asks to calculate what the printer's value will be after 6 years. So t is 6, and I'm looking for f of 6. Again, said this like 17,000,000 times in this video, but I just copy down that exact same thing, and then I raise it to now the 6th power because I just have to replace t with 6. And when I do that, my answer comes out to 1114.57. Now take a minute to think. What are my units here? What is the context of this problem? Well, reading the problem, my initial value was given in dollars, $2,400, and I'm asking us to calculate the printer's value, right? How much the printer's worth. That is money. So I will leave it rounded to the hundredths place, and I will add a dollar symbol in order to give the units so that this makes sense in context. So now that you've watched this video, you should understand how to model exponential growth as well as exponential decay and being able to write the formulas for both.